Hey, I'm Nathan Mikulski, and today's topic is springs. Let's jump into it. So, we have a lot of things. We have some things to talk about springs that you may or may not know. Let's kind of start off with something a little more general, like what are springs? You know, springs are devices that are used to compress. They usually look like a helical or something like that, but they're usually either compress or stretch to either slow down, speed up, or resist motion. Now we have 5 general types of springs that we'd like to discuss. Let's talk about first compression springs, which is, think of a helical spring, like a normal spring that you'd see in like kind of like a slinky or underneath your car, where you compress it and it serves to resist something. Then we also have torsion springs, which when you twist will again either will resist or like add to the motion. And we have variable springs, which will be able to change their resistivity or additivity as they are compressed, and some of that would stem from, say, material properties in spring design. Tension springs, which is pretty much the opposite of compression. Instead of compressing something, it'll serve to stretch it, and as it stretches, it'll slow down something. So think of like 2 ends on the side of like just a spring, right? And as one would go this way, one would go this way. As you pull apart the springs, force gets stronger, and it becomes harder to move those two. And then compression, torsion, and tension can also be constant, which means they'll have just the same force applied to it as throughout the spring is stretched. Now let's talk about key diameters of the spring. There's 2 key diameters of the spring, and in this case we're going to be looking at helical springs, and we'll most likely be looking at helical springs throughout. Now there's 2 key diameters when it comes to helical springs. Now see, the first diameter is D, or capital D. We'll call it capital D. The capital D represents the distance from the center to center distance of the spring. As seen here, center distance of the big coil of the spring, or center to center of the wire, right? And then we have little d, which is going to be the diameter of that wire. Now there's other diameters you could throw on from this stuff, like a outer and inner diameter, but those, I guess, are less important to our calculations and can be used to find this D, or this capital D, which is the center to distance again, and the little distance. Now there will be another equation later on that we can use to relate big D and little d also. Now let's move on to the stress in helical springs. Stress in helical springs can be given by this equation, where tau, or your stress, is going to equal to Ks, or the static spring constant, times 8Fd over pi d cubed. Now that's kind of a ideal max stress in helical spring case, but let's look at a case where like it'd be actually bending. So we replace our Ks with a Kb, or that coefficient Ks with Kb, and leave the 8Fd over pi d cubed the same. Now you might be asking, what is this Kb? Well, here it's the spring factor when we take into account the bending of the spring. Now what does that equal? It equals 4c plus 2 over 4c minus 3, and that c is big D over little d, which is the equation I just talked about that could relate D to D. Now, one more time, Kb, or the main Kb that we were interested in, or main helical shear stress we're interested in, is Kb 8Fd over pi d cubed, little d cubed, sorry. Now, one more thing we should look at is the deflection in helical springs, which is we're gonna approximate our K to be d to the little d to the 4th times g, which is a material property, over 8 big D cubed over Na, and Na being is going to be the actual number of turns in your spring. Now, one more thing we gotta consider with springs would be stability. Stability is when your length knot, or your initial length, your starting length, you may call it, is going to be less than your critical length, or which can be defined by pi d over alpha times this quantity to the 1/2, and the quantity is 2 times E minus G, both of which are material properties, over 2 G plus E, again, material properties. Now, when we have steel springs, we can approximate that to the L naught had to be less than 2.63 times big D over little d, or 2.63 times your C. Now let's apply all of these to an example. Let's look at this. Let's look at this example. We are asked to design a spring, or a helical compression spring. Remember compression spring and helical spring, like we talked about, with a max force applied to it of 20 pound force, or 20 pound-feet of force. It's going to be compressed 2 inches. The static length will be 1 inch, or it should be no greater than 1 inch, and the final length should be no greater than 4 inches, or the initial, or the starting length should be no greater than 4 inches. And our NS is going to be 1, 2, and it will be squared and grounded at both ends. Now, how can we tackle this, or how can we make it a string using these properties? Well, we can kind of look at an alternate equation value of K. Remember, K is just your spring constant, so it can be, and you can find that from force times, or force equaling K times X, or K times the distance, or sorry, the spring constant times the distance that the spring is stretched. And rearrange it simply to find K, knowing our F and our initial compressed distance, which we will do here, and we will divide our force of 20 pound-feet of force divided by 2 inches, and we'll get 10 pound-feet per inch, right? Now, we're gonna kind of bounce down here for a hot second, and we're gonna see that we are gonna try to find our K, or we know our K, we're gonna try to find our actual number of turns using this equation, but to get to this equation, we need to know a few values first. So let's jump back up here, and remember that we find with our SSY is going to be equal to 45% of our ultimate strength. Remember, which is equal to 45% times A over D to the M, which in this case will be 45 times 201,000 divided by D to the 1.45. And since we are not given a D, we can't really find a D off, so we got to try something. Let's try plugging in D is 0.08 inches. And we're going to use this as a good guess based off of some of the tables that we were introduced to in lectures. Mainly because we can define all of our values without running into any issues with this small diameter. So plugging that into this equation, which these values are also found off of a separate table from lectures, we will get 130,455 psi. Now, plugging this into this equation, which we're going to have as tau equals our KB times our 8FD over this stuff. It's just rearranged to look slightly different. So remember, this is our KB. So our SSY, which we just found, and our NS, which we're given, and plugging in stuff here. So 8 times 1 plus 8, I believe is what this Greek letter was. Remember that it'll be equal to 0.15 once everything kind of bounced out. It's more of a constant, times our F max over pi d squared, little d squared, times C. Now, knowing this relation, we find that our tau is 108,713 psi. We can solve for everything else in here, since we know our F max would be the 20, and we know our little d from plugging that in there, and we know our constant, and we can get C equals 10.53. Knowing that, we can use this C equals big D over little d relation to find our big D, which would be 0.8424 inches. And then we can rearrange all that stuff to find our KB, which would be 1.128 inches. Now, rearranging to solve for our NA from the deflection and helical spring equation, we can see that our NA is going to equal little d to the fourth times G, remember, is our material property, which can be found from the tables, over 8 times big D cubed times K, which we found here at the beginning. Plugging all that in, we'll have 0.08 to the fourth times 11.75 times 10 to the sixth over 8 times 0.8424 cubed times 10, and that'll all equal out to our actual number of turns being 10.05. I know, how are you thinking? It's like, how are we going to have 10.05 turns? It's just kind of the way the spring's going to work out when we make all the turns. Don't get too hung up on that one. Now, how can we find the total number of turns? Well, we're going to again refer to our table, and looking at our squared and ground conditions, we find this relation from our actual number of turns to our total number of turns, and that is just NT, or the total number of turns, equals the actual number of turns plus 2. Plugging in, we'll get the total number of turns to be 12.05 turns. Now, how is that all going to relate? We can use all these values to find our lengths, and then judge to see if we've chosen values correctly to fit the criteria. Now, let's look at it first as our stretch length, right? Or sorry, static length of the spring, sorry. And that equals to D times NT. So plugging in our D, which we are, remember, guesstimating is 0.08 inches, times the 12.05, we'll get an unstretched length of 0.964 inches, which is less than 1 inch. So that parameter fits. It works with that one, but remember, we gotta check our other ones. So let's check our L naught. Our L naught is gonna be LS plus our unstretched length, or static length, plus the yield strength at F equals F of S. How are we gonna do that? Remember, our LS is gonna equal 0.964, which we just found, plus the 1 times 1 over, I believe I said it was eta, times F max over K. Plugging in, because we know constants, we know our K and we know our F max, we can get 0.964 plus 1.15 times 20 over 10, which is, this is the 1.15, 20 over 10. We can get our original length being 3.264 inches, which is less than the 4 inches specified in the problem. But how do we know if our spring is stable? Remember, from our stability equations, one thing I forgot to mention is that this is a steel wire, so we can use our simplified stability equation, being we can set our critical length is our stability equation, because we're going to compare our critical length to our final length to see if it will be stable or not. So plugging into our steel equation for that, getting alpha from your tables, we get 2.63 times 0.845 over, 8424 over 0.05 will be 4.343 inches. Remember, our L naught, our original length, is 3.264 inches, which is going to be less than this critical length of 4.43 inches. Therefore, our spring is stable. Now, hopefully, there are other applications we can do using variations of our other equations, and we can find other various properties, but that is the main gist of our spring problems. Thank you for your time. I hope you learned something.